first, thank you to the sponsors of the conference for everything they did to help. And this is the summary of our session. So the main goal is to give you a better insight of what it is. And we'll do a tour of different AI domains for that. It's not necessarily going to be super sexy, but I hope that you get new things out of it. And, well, we'll see. So the intro will be about what is AI, and we'll see that the interesting way to deal about it is to think about agent system. And then we'll look at the DNN environment in which I'm going to illustrate a couple of those concepts. And then we'll go through those 4 domains, which are quite related, and we'll see that. But we can see them one after each other. So the first is problem solving, and then reasoning, and then dealing with uncertainty, and then machine learning, which concerns pretty much all of the above, and there's a lot of relations between those domains. The motivation for this session was double. The first one is I've just finished giving a course about AI in an engineer school in France, which is called ORT. I've animated the course in an online place. Well, it's in French, but there's a lot of resources if you want to access it. It's online. And it's mostly based on a book. And this is a book. In French, it's like the AI Bible that nearly all the professors are following to give the course. And it's really well-written book. I've got it in PDF somewhere here. If you want it to have a look, well, I can give it to you, but yeah, I highly advise to buy the actual book if you're interested in going further in the field. And the second motivation is a module, a DNN extensions that I've been developing for several years now. It's called Portal Keeper, and it's hosted on Codeplex. The source code is also on Codeplex, but I might probably move it to GitHub sometime later this year. And it's an agent system. So far, it hadn't dealt so much with artificial intelligence, but this is the next step that I'm currently implementing. And I designed the course to be taught on DNN with that module. So all the stuff that went into that course, it went into that open source DNN extension. And the last motivation is the next plan. The next plan is for me to kind of do a spin-off of what I'm doing at the moment in the DNN company and start that new project, which is going to be called My Intelligence Agency. And the goal is to sell artificial intelligence services online, maybe in a bit the same or different way people like Microsoft or Zapier are doing, and try to find a niche market within that. So hopefully some of you guys are interested in the field, and if you are, then feel free to come to me. I'm looking for people to teach. Like that teaching is something I really want to do again, and maybe for partners and people to move along with. What is AI? Well, it's a difficult question, and it's a debated question in the field. One interesting starting point would be that seminal article from Turing, Computing Machinery and Intelligence, where it talks about the Turing test and what AI could be and what it could be in the future. And it's in the 50s, so it's quite interesting to read. But mostly the definitions of AI fall into 4 categories, which are thinking humanly, thinking rationally, acting humanly, and acting rationally. And basically, what seems to be the most useful approach about it is acting rationally, because thinking is not necessarily for intelligence. And you could think of thinking as the act of thinking amongst other acts. And humans are not like the only source of intelligence, and we realized that rationality is a better way to talk about intelligence. So acting rationally and the moving into that understanding of the field, it naturally as a consequence of trying to figure out how to build rational agents. So that's what we're going to look at. The foundations of AI, quickly, well, there's a couple of fields that come to mind. Well, computer science, biology, cognitive science, obviously. But it's actually much more intertwined and really deeply with massive other fields in science. And it relates to a lot of complex questions in mathematics, philosophy, economics, psychology, linguistics. So this is something that is a bit less known. The history of AI, if you want to do that quickly, the early stage, which was the early stage of computer science, was really enthusiastic, and there were really amazing programs which you probably all of you have nowadays every day on many software in your computers. But at the time, they really thought they were going for the moon. And then in the 70s, there was a crisis period where they discovered that all those problems that they were solving, they didn't scale up, really. And there was a complexity issue that prevented them from reaching the moon that they were aiming for. So this is a period when neural networks, for instance, that had a really early start at the same time as the early computers, they nearly disappeared from the research. And then they came back. In the 80s, became an industry with robotics and planning being everyday tools. Neural networks come back to popularity when we learn to train them deeper. And then in the 90s became the science and really related to those other fields. I'm talking of became of merging with the equivalent field, like in math, in philosophy. They were all talking about AI. They needed a common vocabulary. And the last trend, which you probably heard about, is deep learning and smart contracts. But we come back to that later, and we go through that kind of history through the different domains. AI is everywhere in your everyday life. Well, all the public services or customer services and everything technological nowadays is having more and more AI. It could be early AI technologies that we don't really consider AI anymore because it's so ubiquitous. Or it could be last trend, deep learning technologies, but you got AI everywhere. So let's get back to this agent notion. What's an agent? Formally, you can define it as a function that maps from a percept's history into actions. So you got a system that perceives an environment through sensors and that acts on this environment through effectors. And that's a simple definition. You could start with that and then make it richer. So the easiest agent would be what we call a simple reflex agent. You got sensors, you got in the information from the sensors that goes directly to a decision process, which is made of conditions and action rules, and then goes into the actuators. You can make it a little more complex by adding states. For those who were here at the previous session, Peter was manipulating a lot the state and was an important concept in React. Well, in all agents, a stateful agent can do a lot more than a stateless agent. So, but it's still condition, action, rules, and that drives us to the environment where we're going to experiment. So this is DNN within the .NET stack, and with a small focus on the components in charge of rendering and dealing with the HTTP requests, which are handlers. And we're going to add Portal Keeper to it. And Portal Keeper, what it does, it adds 5, or actually 6, but 5 main agent systems at different points in DNN. So this is entry points when you can inject agents with intelligent system, but we look at web services, web API services, and the reason we look at that is that when you got a web API endpoint, then you can turn it into whatever you want. So we'll concentrate on those things, but you have to keep in mind that what we look at, you can apply it at the firewall stage, within the scheduler, in an automaton, or in a control adapter, or in a handler, in a call from a JavaScript application, whatever you want. So let's look at the environment. We'll look at two things. First, Portal Keeper. I'll do a really small presentation. And then we'll move to Postman. Postman is software to run HTTP queries. So it's very practical to test your web API services. And we do most of the experiments in Postman, which is there. So this is the not too sexy part of the session, because I assume that the user interface is something you talked a lot about, and it's not really the topic of that session. So we'll concentrate on what the services do, and we just test the services, but then you can put them behind any user interface that you want. So those Postman, this Postman collection is available together with the module online. So you can download it, and then you have a lot of sample HTTP requests to test the different services. And this corresponds to the AI part of Portal Keeper. So this is the main configuration form of Portal Keeper. You find the different kinds of agents that you can build. We're interested in the web services, and in web services in the artificial intelligence service. And here is a collection of controllers that will demonstrate. So we got search, games, constraint satisfaction problems, propositional logic, first order logic, probability, neuro, and Go for the game of Go. It's still a work in progress. There's 2 volumes of the AI release, and volume 3 will include some of the stuff that we'll only talk about, but I'll try to be as exhaustive as possible. So there's things that you won't find yet on those services, but we'll talk about them. So where can we move forward from that rule, action, condition-based rules? Well, the earliest step is to set goals. You replace the reflex system by one where you set goals and you try to find solutions for those goals. So how do you deal with goal-based agents? Well, the first thing is to properly describe them. So what is the goal to be achieved? What are the actions available? What is the state's representation of my problem and the solutions? And then I'll try to find basically a path from the initial state to the goal state. This is the first way to look at things. And this is the way animals and a lot of systems look at things if they don't have something better to do it. So let's have, for example, robotic assembly, where the states will be the coordinates of joint angles, the part of the object to be assembled, and the actions, the continuous motion of robot joints. The goal test will be the complete assembly, and the path cost the time to execute. But you can replace that with any problem that you might have. The state will be made from, I don't know, user profile, properties, the actions, something that you want to display, or some workflow that you want to activate. And you can set goal test as well. Another type of examples are toy projects. There's a couple, and the 8 puzzle or chess at some point, or like the 8 queens problem. There are toy problems which are interesting because they look simple. They're not that simple actually, and they're quite interesting to study searching strategies and AI components, because you can measure things with those. So this one we'll use it a bit later. The 8 puzzle problem, you got location of tiles, and you can assume you're moving the blank tile left, right, up, or down. This is the actions. And the goal state is given. And it's an AP hard problem, so you can make it larger and then it gets complicated. So you start with what we call uninformed search, where it's more or less blind search. You have to decide the way you're going to try the solutions, but you do whatever you can. This is, for instance, a bidirectional search when you start from the start point and the goal point and you try to find a reaching path. Then you have informed search, where you use heuristics. Heuristics are functions that give you an information about how far you are from the solution. So of course, if you have a heuristic, you can greedily go for the goal. And this is, for instance, the A-star algorithm that does that. And then adversarial search is important when you have other agents that will work against you. And if you want to think about that, then you will have to emulate your opponent's thinking, one turn out of two. And this leads to trees. We call them minimax trees, and this is an example. So basically the way to look at the game with the other tools that we're going to look about. And then constraint satisfaction problems. There are problems where you want to satisfy a set of constraints, and we have powerful tools to solve those problems. So maybe this is the first kind of problem that you might bump into. You want to satisfy a set of constraints from your customer, for instance, and you don't have the exact solution. You want to look for a solution. Well, then you might use artificial intelligence. So second demonstration. The first one is not on DNN. It's a JavaScript library, but I find it quite good and illustrative. So let's look at that. Well, here it is. So you can choose your algorithm, and then no internet anymore. Well, if I don't have internet, I won't stay long on that. It's just a pathfinder. You would see the you would see the pathfinding process on screen. Okay. Yeah. And then on, so that was for the client side, but well, if you get to the slides, you have the link inside, just look at it. You got different algorithms, and on the server side, you got them in those three controllers. So you got search, games for adversarial search, and CSP for constraint satisfaction problems. So if I look at search, I have a demo action, well, simple action that just gives the default strategy applied, and one where you can pass the strategy as a parameter. And as default problems, you have the 8 puzzle, where you can choose the heuristic applied, you can shuffle the puzzle, and the other one is the n queen problem, where you try to fit n queen on a chessboard. And 8 is quite easy. I mean, it's not easy for a human, but it's easy for the computer. But if you input 20 queens, it starts to get a little messier. And again, you can choose a heuristic if you're using informed search. And that was for the demo problems, but again, you can change those problems and put yours in place. And the default strategy, you can choose whatever informed algorithm you want. So you got A-star, this is the most famous, but other ones, I'll talk about hill climbing in a minute. And you have to choose if it's a graph search where you account for cycles, and tree search where you don't account for them. And you got uninformed search, the same way you can choose the algorithm you want. So if we look in the Postman manager, and I try the default search, Okay, so this is the output is quite verbose, but it's for the matter of the demonstration. You can, of course, you can change the services if you just want a very concise JSON. This one gives back if it managed to find an answer, the search duration, the action numbers, and then metadata. The search strategy was informed A* graph search. The problem was 8 puzzle with that initial state. And the heuristic was Manhattan because we used informed search. And this is the solution actions that lead to the final state, which was the goal. So, well, it was an easy example, but you replace that with a complex problem, it should work. And then, well, you have other requests that test the different algorithms. So you can make experiments on your own. Then on the game side of it, let's see. On the game, you got similarly demo games. So there are 2 demo games, Tic-Tac-Toe and Connect 4, which are, again, simple games, but they give you the idea of how to deal with your own adversarial search if you need that. And the strategies, you got minimax, alpha beta, iterative deepening alpha beta, and one that is particular for Connect 4. Well, this is very simple ones. If your game is complicated, iterative deepening alpha beta is what you will be looking at. And finally, CSPs. So you got demo actions, and you got one which is solve. And from now on, when I made this one, I tried always to come out with a general solve action when you can pass the problem as part of the HTTP query. So with those kinds of service, you really don't have much to do on the server side. Let's say, well, games demo would be just playing a full game of Tic-Tac-Toe against itself, I think. Yeah, got it. And then CSP demo, it is solving the map coloring problem. Well, it was there, where you want to just color Australia using only 3 colors. Well, it's not that trivial. Like, you can get it wrong. You might get it right, but you can get it wrong. So it's a simple constraint satisfaction problem. And it gets sorted here. And we got the same in dynamic mode, where the where is that? No. Here. If I look at the body of the request, the problem is passed as a parameter. So you've got colors. For instance, this is the color class from system drawing, non-color. And then the variables, and then the expressions, that kind of expression. So this is basically .NET code. It could be anything you want, and that's quite interesting. Okay. So a couple of other things about search. One interesting class of strategies are what we call local search, when you don't really know what the end goal is, but you're going to look around the solutions that you get and try to find if there's a trend, if there's a gradient which you can follow. So we call that hill climbing or gradient descent. Well, it depends on the way you look at it, but basically you kind of try to explore the solution landscape and find global maximas. And one problem that you might have is you get stuck on local maximas. So there's a couple solutions for that. One is called simulated annealing, and means you're going to keep the algorithm searching like a hot metal, and then make it more calm and settle down. And hopefully it will not settle down early on local maxima. And then what we call stochastic beam search, which is when you have several agents searching at the same time. Like it's not one algorithm searching, it's the algorithm searching in many places at the same time. And the most refined version of that is genetic algorithms, where basically it's modeled from the natural selection, where you got selection, mating, crossover, random mutations, and you have to define a genetic before you can apply that. But this is basically stochastic beam search refined a little more. And we end up with that being like the most blind way of looking at solutions. So sometimes you might end up having to implement a genetic algorithms, but that's usually when you don't know much about what you're looking for. But this is not the way the computer works. Usually it's not working as a bee finding its path. It's not working as nature evolving. It's much faster than that. It uses much less resources than that. And that's because of knowledge and reasoning. Usually computer, we get input sentences and give conclusions, and that's enough to interact with the world. So this is the second stage of our exploration. And one important thing will be the way the states are described. In search, as we just saw, the states could be atomic. Not much information about the state except that you're moving from a solution state to another one. And then you can factor it with different characteristics, and the ultimate representation is a relational structured representation. But it's a trade-off, because you cannot search things as fast with structured representation as with atomic. If you look at them in the same way, you have to look at them a different way, and then they're faster. So the first thing that we can use is propositional logic. Here is a BNF form of propositional logic as a grammar. And by the way, if you want to use grammars, use Grammatica. It's really the best tool on the .NET environment to do that. Propositional logic, and as you can see here, the set theory interpretation of it is grounding most of computer science, and this is pretty much the only thing you need to make a computer logic-wise. But the thing, and then it works on the idea of proof, like mathematical proof, where you will define correct rules of inference, and you can go back to Plato or Aristotle to talk about what the correct rules of inferences are, like rhetoric and politics. It's all very important in those things. And then when you have correct inference rules, you will have a sequence of sentences derived by those rules, and the last one of which is a theorem that you want to prove. So a simple example, if humid is a premise, humid implies hot is another premise, then hot by modus ponens is the theorem. We've got a more complex example on the right with variables, and this is backward chaining reasoning, which is quite similar to some stuff we usually do, but there are other inferences that are much less natural, and it's nice that the computer can use either. But it lacks a bit expressivity. You cannot describe the whole of mathematics with propositional logic. So we come out with another more complex logic, which is first-order logic. And first-order logic adds a couple interesting components. Quantifiers for all or exists, and then constants, variables, predicates, and functions. And this added to propositional logic is much more expressive. And it gained traction a little before object-oriented languages went the same path, basically. So you can think about it that way. And then you can even add other orders, like you have higher order logics or model logic, temporal logic, fuzzy logic, where the commitments in terms of what exists and what's the nature of the knowledge changes between the different logics. So let's have another demonstration about logic. The two controllers you have for logic are propositional logic, where you have a demo action and an ask action. Again, the demo uses the demo data, which is there. The default knowledge base in propositional logic is, well, quite random, really. But you replace that by information that is critical for you. Things you know about your customers that are from the cookie or that kind of things. And it still works. And then you can choose the inference procedure. And again, there are quite a few procedures you can choose from. Some of them a bit longer, but more resilient to complex problems. Some of them, you have to have a simple problem, but they're very fast. And we've got the same with first-order logic. So again, demo, default knowledge base, and ask, where you pass the knowledge base as part of the parameters. And the default knowledge base is a kind of Cluedo problem, where you define the actors, the predicates, the facts, and then you want to know who's the criminal. And it's under, well, we'll see. Where is that? Yeah, the default predicate is who's the criminal. So if we look again in Postman at the corresponding queries, so the demo for propositional logic, it gives a true inference with the different sentences. I'll get past the other inference methods, and then in first order logic, here's it's interesting, it adds also the proof that leads to the answer, and the answer was Colonel West is the criminal. Yeah, this is quite powerful, and included in the available inference procedures is an author-like theorem prover, which actually proved a mathematical problem in the early 20s that mathematicians couldn't prove. So it's very robust stuff. Well, that's it. So back on our slides, the last bit that you can add to this knowledge representation domain is semantic web. And this is, I suppose, the part that you all want to know something about in the coming years. It's something the W3C and especially Berners-Lee have been pushing for a long time. And I suppose you guys are more familiar with the representation stack that you can build from XML or from JSON, or maybe with the communication stack that you can build from that. But there's also a semantic task that you can build from XML, and this is probably the one that they've invested the most effort in, and it is just coming now as something that you can use in your everyday web designing, adding semantic tags or that kind of things. But there's a really huge work on that part. And basic building blocks are RDF documents, resource description framework. So RDF documents are made of triples, which are facts built like subject, predicate, object, and they're interpreted in the software that manipulates it. And this is the idea. The three are interpreted within the software. And then you got modeling with resource document, which is the most important thing. In .NET, the two components which are interesting are .NET RDF and Brightstar DB. One is for manipulating RDF, and Brightstar DB is a database, semantic database. They are both open source, really good components. And the idea, the end goal and the end game for semantic web is that all the data on the web is interconnected through services where the agents communicating between those services, they know about the semantics of the data they manipulate. And if you need an information about whatever fact in the world, you just go to Wikipedia to get the information about it. And you don't need to parse the page because Wikipedia gives you exactly the right structure of information that you want. This is the principles behind semantic web with the proof material that we just talked about, which is allowing to make generalization and to have real conversation between agents. And the top layer is trust. If you add cryptography, then you can build trust from proof. And this is what you get in blockchain, for instance, and smart contracts more generally. So this the top levels of knowledge representation and using knowledge-based systems. But the world is uncertain. So you got uncertain inputs, uncertain knowledge, uncertain outputs. And the conclusion for that is that you want to use probabilistic reasoning. And the sub-conclusion is that from now on, you're going to have probabilistic results. And this is the thing that are the most useful, because all the certain stuff that we talked about is usually very simple cases, and you have to have something more robust to uncertainty. So decision-making with uncertainty becomes, and rational behavior becomes, for each possible action, you identify the possible outcomes. You compute the probability of each outcome, you compute the utility of each outcome, and you compute the weighted expected utility over possible outcomes for each action. And then you select the action with maximum weighted expected utility. And that changes our goal-based agent, which becomes a utility-based agent approach. Probabilistic programming, it's mostly grounded in the naive Bayes interpretation, where you use the Bayes equation, diagnostic equations. It's called naive because you assume independent phenomena. And then you can use the diagnostic equation. So if you got the prior probabilities for the causes and the conditional probabilities for the effects, knowing the causes, then you can get the diagnostic probabilities. From there, if you stop ignoring the dependencies and you add them to the picture, you get Bayesian networks. So if the fact that an alarm rings depends of either there's a burglary or an earthquake with different probabilities, and then that as the consequence of John or Mary calling me, then when I receive a call, I can try to figure out if it's rather a burglary or an earthquake. If you add dynamic or temporality to this, then it gets really interesting. And the best example for that is Google 1.0 PageRank. You can think about it like an agent on a web page can follow random outlink with a probability. And over a stationary distribution, it will end up spending more time on the highly reachable pages. And there was the first way to fight link spam that Google came about. And well, we know where it ended up. So temporal Bayesian networks can be very powerful. Usually the idea behind that is you use Markov processes. And Markov processes, which can be represented like that, are stateful systems where you got state transition probabilities, but they all have the Markov property, which means the future state only depends on the present moment and not on the past. All the past is contained in the present moment. And we usually assume most natural phenomena have the Markov property. You can add one level of complexity where you think, well, I don't know really about the state. I only know about the evidence I've got about it. And this is hidden Markov networks, where the state itself is only something you can assume conditional probabilities with evidences. And you just have evidences as data, but you can still reason about it and figure out what the probabilities are. So let's see just a simple example of a hidden Markov model. It's a hidden Markov model of rain, where you don't get to see rain, you just get to see if people have umbrellas, like say a camera from inside and wants to figure out if it's raining outside or not. And you can have the probability that it rains at instant t if it was raining at t minus 1, and the inverse. And then you can have the probability of umbrellas if it was raining or not. Those probabilities, you can get them through data experience. You collect the data and you get access to those probabilities. And the hidden Markov model will be defined by the initial distribution, the transitions, and the emissions, the evidence that we'll observe. And let's see what it looks like. So this is going to be the probability controller. You have a demo for base and several demos, and each time also the ask action. And several demos for hidden Markov models or dynamic Bayesian network. And this is what a hidden Markov model should look like. Here we go. So the model's got state variable, rain t, umbrella t, transition models, where you give the probability, sensor model, prior distribution, and then there's the query that's getting passed. You give it a series of observations, well, umbrella, umbrella, not umbrella, and then it will try to figure out what was the actual state. What was that? Fixed lags moving. And here is the estimation probabilities of whether it was raining or not. So again, very simple, but you add complex data, should work as well. Okay, well, real hidden Markov models examples. We just talked about PageRank, but you all use Lucene.net on an everyday basis. Or OpenNLP, maybe. OpenNLP is about grammatical parsing of sentences. So this one is the Java one that the port of which using EKVM is pretty nice. But you got others that you can use. And it's an interesting point because it gives you a bridge between text and semantics, which Lucene doesn't really. I mean, we can do something about it. I'm sure some of you have experimented in that. But having the actual grammar of sentences and knowing what the subject and the object is really important. And that gives also, if you add layers of dynamic Bayesian networks, you can have speech recognitions and machine translation, and of course, Microsoft Cognitive Services are interesting for that. We had a session with Joe and David about the BOT framework using cognitive services to talk. Well, this is the kind of technologies. Another one, interesting, radar tracking. One of the first one that's been implemented is, this is early stage where it was obviously quite important. But all of these, they are trained probabilistic networks. You give them a training set and you want to find the hypothesis that best matches the training set. So this is about learning, and we're going to talk about learning last. But just a quick review. Infer.net is the best tool in the .NET environment to learn dynamic or static Bayesian network. It's really amazing. You got a lot of documentation. So it's your go-to tools if you want to start data mining and making hypotheses using that kind of approach on your own data. So learning, different learning tasks. So there's so many things that machine learning can bring. Well, I won't go through all of this. I'm sure you're all aware of those. So this is our learning agent, and it is not contradictory with what we've seen. This is something you can add to reflex agent, or a model-based agent, or utility-based agent. Learning is something that you can add to something else. But it adds specific components, and this is the most complex one, where you have a performance element and learning element interacting to change the way the agent works, but also a problem generator where your learning goes. So you don't have to do all of this to implement learning, but this would be the most complete learning agent. Inductive learning, learning by examples, is the art of constructing consistent hypotheses to agree on a training set. And one example is regression, where you're going to try to fit a curve on points that you have. And there's a general principle, which is Occam's razor, and which is to prefer the simplest hypothesis consistent with the data. And there's a lot of small things in the algorithms that we're going to see that are related to that principle. Another important inductive learning problem is classification. In regression, you were in a continuous valued environment classification. You have classes, discrete classes. You want to separate the data in those classes. This is linear classification. One important point with classification is you can use higher dimensions. For instance, this is hard for a linear classifier, but if you add one dimensions, then you can separate the points. And this idea, you can have it in a lot of machine learning system, the way you project your data in higher dimensional space, and then do some simple calculus in that space, and then get back to your very famous example of inductive learning, machine learning systems, and one that you can use for classification. They have a biological inspiration that was addressed in the early 40s, so this is things that have been worked on for a long time. And a biological neuron will have many input synapses, a body that will integrate the input information, and then an axon where sometimes it will fire provided there was enough input. And the way you translate that in useful mathematical objects is you assume the synapses are weights that you're going to put in a matrix column. And then all of this is summed, and you have an activation function, a squashing non-linearity that will allow it to learn. And with a single neuron, we can already do some linear classification, but then you're going to add layers. And if you look at the pictures here, this is the expressiveness in terms of classification that you can have with one hidden layer. This is the one that you can have with two hidden layers. And you can see that coming back to that image, if you add hidden layers, then you're going to be able to do some more interesting stuff. Deep learning. So hold with me. This is the most complex things that we talk about. The recent trend, there's two things in there. The first is convoluted networks, which are actually not that recent. They were invented in the 90s by a French guy who's head of Facebook's artificial intelligence now, Yann Lequin. And the idea, they were modeled on the human vision, where the idea is you will have regions convoluted over the surface of inputs like you've got in the eyes. And this will lead to tensor kernels that you will multiply over your, this is like just an eye. Let's say it's a pixel bitmap of what the eye sees. So you're going to convolute these kernels, and those you're going to add
subsampling, where you reduce the dimensions of the input. And this has a consequence of making it robust to changes in orientation and scale. Add to that better, computing power first, and then better algorithms to do gradient descent with that. Then you can train deep natural hierarchies, where we used to have feature extractor and mid-level features where we would classify. Then you can classify over all the hierarchies of your objects. And it works because nature has object hierarchies. Nature is highly hierarchical. And this is, for instance, the resulting trained kernels that you can see at the different levels. And it's really amazing to see that at low level, the kernels have learned to detect edges and orientations and colors. And at mid-level features, you can see the beginning of shapes, whereas at high-level features, they have concepts. And those concepts, you didn't have to put them into the system. The training algorithm, they're powerful enough to derive the high-level concept themselves, which makes it really revolutionary. So, just to finish, an example of the game of Go. So maybe you guys have learned about the recent match between Google's AlphaGo and world champion Lee Sedol. Was really interesting to watch if some of you are familiar with Go. And it's an interesting game, and it replaced chess after Kasparov lost in '96, because it's basically harder. It's got a higher branching factor that makes it more complicated to do brute search or that kind of solutions. And it makes it really interesting for nowadays level of technologies. This was done with Google's framework, which is TensorFlow, and Microsoft has been competing with Google and Facebook to instance, but Facebook is releasing packages for Torch, which is another deep learning toolkit, whereas Google and Microsoft are already on the front edge of deep learning toolkits. And like last year, Google won the competition. This year, Microsoft. Next year, probably going to be Google. So they're really, and they put a lot of effort into those open source software, and that's quite amazing. The last demo is about computing value maps. There are two deep neural networks in AlphaGo. One is trying to decide what move to play, and the other one is trying to figure out what's the situation. This is the one that we're considering now. And this could look, all the squares that we see could look as gain territory by the end of the game. And if you have that, then you can evaluate your score and figure out if a move will make your score get higher or lower. So it's a very important part, and you can actually run an algorithm with just that kind of value function. Unfortunately, I won't be able to demonstrate all of this in DNN, because by the time I trained the network, the last version of CNTK wasn't supporting training on a GPU and running on a CPU. But the last version from April should be fine, and in the next version of that module will include that. So there are 3 steps in that thing. The first one is to prepare the data. So there's a dynamic action here, which simply will load SGF files from a directory. SGF files are games. Let's see. Libraries, AI, Go. So here's a game, and here it is loaded in a UI. So there's a format for that, and if you play with different libraries, you can transform that. Then it's not that simple, because, well, you have to figure out what you want to train the model. So basically, there's a small algorithm there which calls another program to figure out what's the actual end game from an end game position, because that's not that simple. And then you create a mid-board position with a lot of unknowns, and you will associate that mid-board position to the end game position. I pass the details, and then you've got a couple of files to configure your neural network, basically two files. One is saying how the training and the testing will go, how many epochs you will run, that kind of things. And then you got another file for your actual network architecture. So this is the hard bits. And basically you define the inputs, which are meant from features to train and labels to classify. And then you add your layers through components, like this is convoluted, normed, rectified linear convoluted layer. I have like 9 of them, or even more, like 9 or 10. And then in the end you define what's the square error to compute the algorithm, like criterion nodes, eval nodes. And then you can run it from outside. And I get back from my virtual machine, because again, by the time of that work, it would not work in a virtual machine. You had to be close to the GPU, and it has to use the GPU to run. It should not be the case anymore, so you should be able to use it in a DNN. So this is, for instance, a match. And then I'm going to attach a program that I've generated. And I can use an analysis command that I've created. And well, it takes a little while to load the neural networks, but then if you call it again, it's much faster usually. Yeah, if I go like. So this is the result from a train session. It's not perfect. If you're a Go player and you look at it, you might think, okay, well, it got several pieces that were complex, and other ones it doesn't really got them right. But it was just to make a demonstration. I will try to make it better, but it was not the purpose to make a real good player. And I think that's it. Questions? Yes?
It's more looking at the future. I didn't hear any reference to quantum computers, because theory is that we can never create proper, real AI binary. So we need qubits and quantum fuzzy states to be able to replicate true intelligence.
So the question was, I didn't talk about quantum computing, and some people are arguing that you cannot replicate intelligence with only normal bits, binary components. Well, this is an open question. A lot of people who work in those fields, they think that it might have a couple issues, but digital nature of computation is not that much a problem. There's a speed problem, but given enough computation speed, you can reproduce kind of the complexity of the human. This is something that Turing talks about in his article, which I invite you to read. And basically, the answer is we don't know if we need all of this. And we might need it, we might not. There's a lot of hope in what quantum computing can bring in resolving algorithms, for instance, that are too slow to resolve another way. But it's still very early in that it doesn't really solve that many problems at the moment that we cannot solve another way. So it's quite an open question. Other questions?
when starting from games, there are kind of artificial problems. Interesting.
Yeah, all right.
On the theoretical point, but what kind of example could you give in real life that we might use this kind of tool?
Well, you could want to use it for data mining. You got a lot of data and you want to know some more stuff about your customer. So there will be offline analyzing and learning. But then you can also use it live with a system that can learn from the interaction with the user, either by reasoning about the stuff you want. And for instance, reasoning plus search is used massively in resource allocation and planning. So that's something you might want to do. But then also for everything like learning what is the best outcome. You could, for instance, add to your DNN search module a click-through model which will analyze where your customer are going to click, either on your search result or even anywhere on your DNN page. And from a couple of hypotheses that you do on the way it works, then you can classify the documents and the users much more intelligently. So that would be an example. So data mining and online reactivity. Yes? Yeah, it works a bit particularly because they've solved a lot of slow computation problems additionally to what we've seen. But basically, it's based on the same systems. And there's a lot of small things that make the computational quite particular in Lucene engine, but all natural language processing resources, they're all learned models basically, and when they all use probabilities. The way I explained PageRank, Lucene, it thinks a bit the same. Other questions? Yes.
If I want to play around with this, what's the procedure to start?
Well, I can give you a hand if you want to make the same demonstration that we did. It's all, if you download the last version of Portal Keeper, you will have all those samples and you can start playing with them. But then if you identify one bit in which you would like to invest, for instance, probabilistic reasoning, if you look at the infer.net resources, they're awesome. They will take you by the hand and drive you where you want to go. If it's neural networks, you got, for instance, the guy from ANCOG who's made a book which is called Artificial Intelligence for Humans, together with a neural network library, which is much easier than CNTK. CNTK is a bit like hardcore stuff at the moment. It's only working properly on a CPU, and you still have to do command line training, that kind of things, but you got much easier examples. And well, neural networks, you got plenty of examples in many places. So yeah, I can give you directions if you want on a particular field, because we've talked about many different things which really don't work the same way. So you have to decide where to look for. Well, thanks everybody. And,